1 atmosphere is equal to 1.01325 bar. And that means, this is an easy number to memorize, or maybe if it comes from physics. 1 bar is equal to, can somebody invert that number and tell me what it comes out to? 0.9869 atmospheres. And so a bar is a little less than 1 atmosphere. You guys know about high altitude cooking instructions? For high altitude cooking instructions, you have to increase the time. You have to increase the time because water boils at a lower temperature at higher altitudes, because at higher altitudes the atmospheric pressure is lower, right? And so what I expect is, I expect water, if the pressure is 1 bar, I expect water to boil at a lower temperature than if the pressure were 1 atmosphere. And so what I want to do now is I want to use my Chem 1A knowledge. I'm going to try to use my Chem 1A knowledge to do this. What is the boiling point of water when P atmospheric equals 1 bar? And so if I have an atmospheric pressure of 1 bar, this is the Canadian boiling point of water, right? Because Canadians would use 1 bar instead of 1 atmosphere. What is the boiling point? Is it 100, close enough to 100? Or is it going to be slightly, I expect it to be slightly off. Maybe, what do you think, 99.9? Or lower? Well, let's go ahead and figure this out. How can we figure it out? Well, boiling occurs when the vapor pressure of water equals the atmospheric pressure. You guys have worked with vapor pressure before, right, in Chem 1A? To get just a little refresher here. You guys have used a vapor pressure water table like this. You guys remember doing this? If you took Chem 1A, you would have done this, because we would have done something like this. You know, here's the vapor pressure of water at 22 is 19.8. The vapor pressure of water at 23 is 21.1. The unit's torr. And that means at 100 degrees C, the vapor pressure of water should be 760 torr. And so normally, let's say, normally it doesn't come right at 22 or 23. When you measure the temperature of your water, maybe it came out to 22.8. You guys remember doing this? Or 22.5. If it came out 22.5, then we assume linear, that this changes linearly between the data, so the data points are close enough space. And so if this is halfway between 22 and 23, then this should be halfway between 19.8 and 21.1. And we do something called linear interpolation. Do you guys remember doing that? If it's 3/4 of the way, it would be 3/4 of the way here. And so we could get a table like this, but a table like this, and doing linear interpolation, you know, there's a lot of raw data here. What some people like to do is, rather than putting it in a table form like this, they like to put it in a graph form like this. And so this is the vapor pressure curve of water. So we could do it graphically as well, and we don't have to do this linear interpolation stuff. So we know at 100 degrees C, the vapor pressure of the water is 760 torr, right? And so actually, how many torr are we at here? So can somebody take this atmospheres and divide it by 760? And they'll tell us how many torr. Or not divide it, I'm sorry, times it by 760. 750.1. And so what we could do here is we can graph it, come out to 750.1, and then see what the temperature is. You know, I've used this. I use this to figure out that, you know, like on Everest. On Everest, it's like 1/3 of an atmosphere or something. I forgot. I did some kind of calculation. And, you know, there's high altitude cooking directions. Those high altitude cooking directions are okay for Denver or something like that, because water boils around here in Denver. But you know, if you're on Everest, where would water boil? Down here or something? So let's say you had to cook your pasta. You're cooking your pasta at about 50 degrees C. How long is that going to take? 50 degrees C would be like a hot tub. Something like, maybe this hot tub is hotter than that, huh? Or cooler than that. But let's say if you cook pasta in hot tub, well, maybe it would cook. But then, you know, the higher in elevation you go, the lower the boiling. I mean, if water is boiling at room temperature here, it's going to take a long time to cook anything. So anyway, let's go back to this. Going back to this, if the pressure, maybe the pressure is only 1 bar. Actually, where does the bar come from? Do they have a different pressure? You know, where does the atmosphere come from? I mean, in the United States, is the pressure higher than in Canada? Or is that the wrong way of thinking? You know, since Canadians use bar, well, I don't know if all Canadians use bar, but if Canadians use bar and we use atmosphere, is the atmospheric pressure higher in the U.S. than in Canada? No. The reason is the bar comes from the physics, the physical definition of pressure, the physics definition of pressure. But anyway, let's go back to this, which comes from the Pascal. Going back to this, we could figure it's 750, so we go to 750 and then figure it out graphically, right? We could do that. Okay, that's another level. But you know what? Graphs and tables take up a lot of space. Graphs like this and tables take up like a whole page worth of space. What would be much better is to define this, you know, with a mathematical equation. If we can define this using a mathematical equation, or if we can define the table using a mathematical equation, one equation that defines the whole table, then we can save a lot of room. And so, do you know what kind of mathematical function this is? It's an exponential function. And we can just fit that using like graphing software, or we can fit it in Excel actually. We can fit this and then come up with a mathematical function for this that looks something like this, you know. And so there are different ways we could figure this out. You know, what is the boiling point of water at one? What is the boiling point of water at 1 bar? Sorry, at 1 bar. Oh, here, I just said it, P atmosphere is 1 bar. And so, you know, if we try to fit that, you know, we'd see that the pressure is going to be some kind of exponential function. You know, usually there's some kind of constants that we got to deal with in P, and then some kind of constant up here, and then some kind of dependence on temperature, and it looks like that. Do you remember seeing an equation like that before? Some kind of the mathematical equation for the vapor pressure curve, or the mathematical equation for the vapor pressure table. Do you remember seeing an equation like that? It's a very famous equation, has a name on it in Chem 1A. It's actually named after 2 people. Spelled it. Maybe not. Actually, yes. It would be this blue curve. This blue curve is the vapor pressure of water in the phase diagram. We saw that alone. What chapter was that in? You remember what chapter that was in? Properties of liquids. This has got to be the right spelling here. Copy that. You know, this is nonlinear, right? This is an exponential relationship. But you've done like semi-log plots, right? Or we can make this linear. If we did this as a semi-log plot, we can make it linear, or we could just take the natural log. If we take the natural log of this, let me go ahead and do that. I'm going to take the natural log of P. And I'm going to end up with this, you know, it's going to be this constant. I guess I'll call this constant A, and this constant B. And then I'll rearrange this a little bit. And so I get ln of P is equal to ln of E to the minus A over T. And A and B come from fitting the line, you know, the curve. Plus, actually, since this is multiplication, we'll just do another constant. Actually, I shouldn't call that B, but it's all right. I already called it. I'll call it B prime. Sorry. And then we'll have that equal to B. Plus B, this is going to equal minus A times 1 over T. A is a constant, plus B, where B was ln of B prime. Do you recognize this equation now? Yeah, this equation. And so what they did here was they took this curve, right? They took the vapor pressure curve here and made this linear by just taking the natural log of both sides. And we can make it linear, text here, like this. And so this is what we call, you know, the vapor pressure data plotted as ln of P versus 1 over T. In other words, this would be a Clausius-Clapeyron plot. Sometimes it's just easier to plot things out linearly than, but I don't bother doing linear, I just do it non-linear. In fact, we'll just get the equation. And then with this equation, we do this. We do a common trick. Rather than plotting the data out, we're just going to use 2 data points. Using 2 data points is dangerous. The reason using 2 data points is dangerous because you're much more subject to random error. If we ignore these 3 data points and just say the curve is based on these 2, right, we could be off significantly depending on how much random error. So the more data, right, the more we can average out the random error. The random error would be, some would be below, some would be above, and we can average those out. And so the more data, the better. But we're going to do this. We're only going to do 2 data points. And so here, if we have lots of data points, we want to do a plot of this. This has the y equals mx plus b type form rather than a curve. But for 2 data points, well, if we have the constants already figured out, for 2 data points, we can come up with this other equation. And the 2 data points would be this. we're going to have P1 at T1 and P2 at T2. And so what we're going to do is we're going to do this. We're going to take ln of P2 minus ln of P1, which is going to equal, now A and B are going to do the same in both. So we're going to get minus A over 1 over T2, sorry, plus B minus, parentheses, minus A 1 over T1 plus B. And the B's cancel out. And then we'll use the property logs. We're going to come up with this. ln of P2, ln of P2 divided by P1 is equal to minus A 1 over T2 minus 1 over T1. It turns out when we investigate A further, A consists of just two things. It turns out that A is just equal to delta H of vaporization over R. And so we end up with this equation. ln of P2 over P1 is equal to minus delta H of vaporization over R, 1 over T2 minus 1 over T1. We can either get this from calculation, the delta H, or we could get it from the slope, plotting the data. So we could get it experimentally or just from the data table. And we get this. This is the famous, 12.2 is the famous Clausius-Clapeyron equation. This would be the quickest way to determine the boiling point of water at 1 bar. And so the quickest way is because we know what is this is where the P's are the vapor pressure, right? And so we know one vapor pressure. We'll call it P1. P1, the vapor pressure of water is 760 millimeters of mercury at what temperature? Actually, let's not do 760. Let's just do 1 amp. The vapor pressure of water is 1 atmosphere at what temperature? Everybody should know this. 373 Kelvin. And so what we want is, we want a pressure, not at 1 atmosphere, we want a pressure of 0.9, what was it again, 0.9? 869 atmospheres. What's the temperature equal to? When we solve for the temperature, right? And then we can get the boiling point of water in Canada, even though I'm pretty sure water boils at the same temperature in Canada. They just have a different pressure standard, which complicates things a little bit, right? And so probably we should, what we probably should do is we probably should memorize the boiling point of water at 1 bar. It's going to be a little bit less. And then our error isn't going to be as big because our error is kind of big, 373 versus 370. Well, if water boils at a lower temperature, then our error is probably going to be more in line, right? But we can't get rid of the error because we made an assumption in that calculation. For sure there's going to be an error because we assume that don't vary much with temperature. We made that assumption, so for sure I expect an error. And so I'd be curious to see how big that error is. But anyway, this is the Clausius-Clapeyron equation back in chapter 12. Now we're going to go back to chapter 13 here. We're going to think, okay, there's some ways of making reactions more spontaneous, like changing the temperature. That's an obvious one. We could lower or raise the temperature. But raising the temperature, how much energy does it take? It takes quite a bit of energy. I mean, to boil water takes a lot of energy. I was boiling a pot of water. I timed it. And boiling a pot of water usually takes 10 minutes. So I set the timer for 10 minutes, come back 10 minutes later once the pot is boiling. It takes a lot of energy. Sometimes we don't want to change the temperature. Sometimes we want to make the reaction more spontaneous at room temperature. Is there a way to make it more spontaneous at room temperature? And so we try to think of ways to make it more spontaneous at room temperature and standard conditions. So what we're going to do is we're going to try to manipulate delta G. We're going to retain standard conditions. But we want the temperature to stay at room temperature, 298 Kelvin. And so how can we make a reaction more spontaneous under standard conditions at 298 Kelvin? So if you think about that, it doesn't seem like we have too many options, but we've seen a case like this before where we made a reaction more spontaneous. And the typical way of doing this, under standard conditions at a temperature of 298 Kelvin, if we want to try to make it more spontaneous, that is, make it more negative, we could try coupled reactions. Coupled reactions takes advantage of Hess's law. Hess's law is that you just add up the energies if you add up the equations. We saw an example of this before, like for example, gold. If we have gold here, and we try to dissolve it in nitric acid, this would form gold 3 plus NO gas plus 2 H2O liquids. What's happening with the energy here? Is the energy going up or the energy going down? Enthalpy, let's say. If we do this, you know what? We're going to be doing this under constant pressure conditions, so we'll just say enthalpy for the energy. But is the energy going up or down? How can you tell? Well, right now we just want to do this qualitatively without actually doing a calculation. By looking at it, can you tell, is the energy going up or down? Exothermic or endothermic? What's your prediction as far as the enthalpy goes? Well, actually, think about that and let's go to entropy. Is the entropy going up or down? This should be easier. Entropy should be going up. Entropy should be going up because we're forming a gas here. I forgot, when we form a gas like this, that requires what? That requires work. We're gonna think about that. And so a liter of gas like this, will expand the volume by about 25 liters. I'm not a liter, a mole of gas, sorry. A mole of gas will expand the volume. And so the entropy is going up. Energy, is it going up or down? Well, what kind of reaction is this? Is it metathesis? This is redox. So for redox, we think in terms of what for a driving force? Gas formation? Or stronger to weaker? Stronger to weaker what? Yeah, stronger to weaker oxidized. So the oxidizer on the left is nitric acid or nitrate and H+. What's the oxidizer on the right? Gold 3+. So which one do you think is a stronger oxidizer? Gold 3+ or nitrate and acid? Well, we can take a look. Actually, we looked at this before. In Appendix D. Appendix D, probably around A20, I think would be A24, maybe too far. No, not far enough. A27. What's the strongest oxidizer? Fluorine. Fluorine is a very powerful oxidizer. I used to work with fluorine quite a lot. I'm glad I'm out of the fluorine chemist business. Because, you know, when I was initiated into the fluorine chemist club, they told me about the fluorine chemist handshake. Have you ever heard of the fluorine chemist handshake? The fluorine chemist handshake is like this. The first year you go to the fluorine chemist conference, it's like, hey, how you doing? It's like this. The next year you go, it's like this. Each subsequent year, it's like this. And then you have to retire from fluorine chemistry altogether. But I was lucky. I got out of the fluorine chemist club with all my fingers intact. But, you know, fluorine's very dangerous stuff because it's, you know, such a powerful oxidizer. You just mix it with any reducer and potential for explosion. So, and in fact, fluorine will catch stainless steel on fire. It's that nasty, under the right conditions. But let's go on here. As we go down the list, here's gold 3. Here, but do you see oh, here's gold 3. Sorry. Well, actually, there are 2 gold 3s. Which one do we use? We use the top one. Why? 2 reasons why. One, we always use the strongest. This would be the strongest. And 2, the product is the right. I mean, this is the right conjugate. This is not. This goes gold 1. I don't see nitrate. I don't see nitrate until I go to the next page, and then scroll down to about halfway down, and here's nitrate. And so gold 3 is a much more powerful oxidizer than nitrate. And so we say that we're going from weaker to stronger. If we're going to weaker to stronger, the energy is going up. And so the energy is going up, the entropy is going up. Hey, if the energy is going up and the entropy is going up, one way to make this more spontaneous is to increase temperature or decrease temperature. All we have to do is increase the temperature. But increasing the temperature of this reaction might be a problem. The reason increasing the temperature of this reaction might be a problem is because this reaction has an aqueous solution. And let me tell you, there are some batteries out there with aqueous solutions as electrolyte, and the batteries can't run at optimum temperature. Because what they want to do is they want to run the battery at a much higher temperature than 100 degrees C. But they can't, because if they go up to 100 or above 100, what's going to happen to the water? It's all going to boil away. And so in this particular reaction, we're very limited to how much we can increase the temperature. In fact, if you think about how much we can increase the temperature, it's just from 25 to 100 degrees C. That's it. That turns out to be a tiny range in terms of thermodynamics. And so, yeah, we can make this more spontaneous at higher temperature, but one, it's a lot of energy to increase the temperature, and 2, we can't increase the temperature all that much. And so maybe it's enough, maybe it's not enough. Could be enough, I don't know. But let's see, maybe we don't have to increase the temperature. Maybe we could do this at room temperature. If we could do this at room temperature, that would be quite nice. And the whole concept behind coupled reactions is this. What I'm going to do is this. I'm going to try to find another reaction, because right now my delta G is greater than 0. So if I can add another reaction to this with a delta G less than 0, that would be perfect. So what I look for is I look for things that can react with the products. So like, for example, gold 3, NO, or water. I know something that will react with gold 3. In fact, gold 3 plus turns out to like chlorides. This is called a Lewis acid-base reaction. If I think about this Lewis acid-base reaction, gold 3 is called my Lewis acid. Chloride is called my Lewis base, but the Lewis bases in this type of reaction get a different name. Do you know what they're called? In addition to calling them Lewis bases, we could call them, it also starts with an L. Not Lewis base, but In fact, we'd stop calling it chloride. We'd start calling it, because what we're going to form from this reaction is this. It's going to be gold with 4 of these chlorides attached. So gold is +3, chloride's -1, 4 of them, so the net charge is -1. What do we call this species that formed here? Tetrachloroorate 3. This is called the tetrachloroorate 3 ion, and we stop calling it chloride, we start calling it chloro because these Lewis bases are called ligands. And so this is Lewis. It turns out that this complex formation, is it favorable? Are we going from stronger acid to weaker acid, or what's going on? How do we figure out what the driving force for this is? You know, and it turns out for Lewis acid-base reactions, figuring out the driving force is much more complicated. In fact, typically for Lewis acid-base reactions, we use HSAB to try to figure out the driving force. Do you know what HSAB stands for, the acronym? Yeah, that's good. Hard, soft, acid, base. This is hard, soft, acid, base theory. Hard, soft, acid, base theory is like a simplification of the mathematics of quantum mechanics to make this more intuitive, so that you don't need to do a computer calculation, you can just try to figure it out in your head. And what it boils down to is this. Do you guys remember LCAO? Another, HSAB, you know, you're not responsible. HSAB is beyond the scope of this class. HSAB, I just wrote that little footnote in the PowerPoint about HSAB. LCAO is important though. You should know what LCAO is, because that's the main thing that came out of, one of the main things that came out of chapter 11. LCAO. Yeah. Linear combination of atomic orbitals. That's what we're doing with molecular orbital theory. When we look at these complexes, remember, does valence bond work or fail? It fails. Since valence bond fails, we must use molecular orbital theory. What's the heart of molecular orbital theory? The heart of molecular orbital theory is LCAO. LCAO is this. What makes a good combination of atomic orbitals? If the atomic orbitals are roughly the same size, that's a good combination of atomic orbitals. If they're lopsided, like one's huge and the other's tiny, then that's not a good combination. And so we give names to it based on polarizability. If something is easily polarizable, that means it's easy to distort the electron cloud, right? And so think about this. Big orbital, like a 6p orbital, versus a small orbital, a 3p orbital. Which one is more polarizable? A big orbital or a small orbital? Big orbital. Big orbitals are more polarizable. So therefore we call the big orbitals soft and the small orbitals hard. And so soft likes soft, hard likes hard, but soft and hard aren't the best combination. And so that means that base strength varies, because if the base is hard, that's one thing, and we can rank them. But if the base is soft, that's another thing, and the ranking is totally different. It's right. And so what this means is this. It's a bit more difficult to predict these types of reactions. It's not so easy. But it turns out that this type of reaction is very favorable, and delta G is less than 0. And so what we're trying to do is this. We're trying to cancel out this. We're trying to cancel out this by using this. So if this were positive 44, we want to make this negative 44 or greater than negative 44, that is in the negative sense, so that they cancel each other out. so that I can get this reaction to go. Now the reaction isn't going to be exactly the same. The reaction is going to be a little bit different, but it accomplishes the same purpose. So for example, I want to dissolve the gold. If I want to dissolve the gold, you know, maybe I don't care what it forms, but I just want to dissolve it. Here it forms gold 3, but in this case, the gold 3 ions cancel. And so when I add up these two equations, I get gold plus nitrate plus 4 H pluses plus 4 chlorides yield, I'm going to get this gold species instead, the tetrachloro orate 3 plus NO gas plus 2 H2O liquids. And then just add them up. And then hopefully it comes out less than 0. Then I've done it. I was able to dissolve gold spontaneously at room temperature. But we've seen this reaction before. Do you recognize this reaction? The bottom one? I'm sorry, what was that? Aqua regia. Yeah, and we did remember we did this already, and we determined that there was no reaction. We determined that there was no reaction because when we went to the chart, it turned out that this was a weaker oxidizer than this. So we're going from weaker to stronger. Remember that? And so it wasn't enough. But anyway, this is helpful because if we didn't do this, then the temperature, you know, if we do this, then we don't have to heat it to as high of a temperature. If we left it at this, we'd have to heat it to a higher temperature because the driving force is much more positive than this. And so, although we'd still probably have to heat this because the entropy is going up, although we'd still probably have to heat this, we don't have to heat it as hot because we're making it more spontaneous. So this is one way we can manipulate the driving force a little bit. But we might try to think of something that's even more reactive. Can you think of something that maybe is even more reactive than chloride? What else does gold 3 like? Tell me some of the chemical properties. What else can you do with gold 3? Reactive with. Maybe not chloride, but maybe we could try different. What other anions does gold like? Well, we could try like bromide, iodide, and see what happens there. See if it forms a complex. That could be. Or we could try a different reaction altogether. This was a Lewis acid-base reaction. Does gold 3 undergo any other reactions? Like what? How about like a metathesis reaction? What things might precipitate? Although we're trying to dissolve it. Well, we might dissolve the gold and form some kind of gold precipitate. What do you think might precipitate with gold 3? Well, chloride doesn't. Hey, how about this? What's the most reactive anion in metathesis? Give me the most reactive anions in metathesis. Nitrate's the least. Nitrate would be the least reactive anion in metathesis. In redox is very reactive, but in metathesis, nitrates, acetates, and chlorates are the least. What's the most? Not sulfide. Sulfide's very reactive, and sulfide could work here, but And sulfide's probably the best because sulfide's soft, gold is soft. And so sulfide's probably very good, but in general, if you didn't know soft, hard, acid-base theory, you would say in other words, what anion would form the most precipitates? These are the kind of things, you look at the solubility rules, after a while you start to think about differences between things and that kind of stuff. But basically, I would say phosphate. Why phosphate? Because phosphates, carbonates, and chromates are all insoluble. And therefore, they all precipitate except for group 1 and ammonium. And out of those three, I'd say phosphate because phosphate's got the highest charge. But anyway, so we could try precipitating out the gold 3 with phosphate. That might be good. You know, we could try different things. But that's an example of a coupled reaction. Let me show you where, you know, this one was not successful, but let me show you one that is successful here. As far, and I'm going out of order in the book because just talk about this. So let's take a look at this. What's that called? Copper 1 oxide. Copper 1 oxide, and this is the symbol for heat. Heat it up, it goes to copper metal and oxygen gas. Take a look at the delta G there. At 673 Kelvin, it's plus 125 kilojoules per mole, meaning it's what? Spontaneous or non-spontaneous? Highly non-spontaneous or just a little non-spontaneous? Yeah, pretty decently non-spontaneous. It's not really much is going to happen here. Now, that makes sense because what's happening with the energy? Is it endothermic or exothermic? It's endothermic. In fact, if you look at the reverse is oxidation of metals. Oxidation of metals is exothermic, it's spontaneous. Oxidation of metals you can think of as like combustion. If you buy a bottle of copper metal, powdered copper metal, do you know on the label what it says? It says flammable. Flammable. Let's see if I have a powdered copper label. Powdered copper metal label. It's copper sulfate. Hopefully on Aldrich they have it. So you buy a bottle of copper metal powdered from Aldrich, and when you read the label, it will say flammable, basically. In fact, I remember like being in, like, you know how Boy Scouts often make fires out in the woods? They bring some steel wool with them. Steel is made up of iron. They ignite the steel wool and gives you a nice little flame, lasts some time. And I know like heat packs nowadays, they have finely divided iron, although it doesn't catch on fire, you know, when you oxidize it, it's highly exothermic. And so the oxidation of metals is exothermic, and therefore the reverse has got to be endothermic. And so let's go back to this, where was I, the textbook. What's happening with the entropy? The entropy is increasing. And so, hey, you know, all they have to do is keep increasing the temperature. If they keep increasing the temperature, then they can get this reaction to go. They just gave up too early. 673 Kelvin? They shouldn't have given up so early. Let's see. You know, let's not give up. Let's try to go for it. We're going to try to increase the temperature until this goes. And so let's do a calculation, because I think they just should have heated it even hotter, personally. And so this will be a quick calculation. We only have 4 minutes left. It better be a quick calculation. It's a quick calculation because the equation is pretty easy. You'll see here. And so we're going to go back to the data table, which is A18. Oops. And we're going from copper 1 oxide to copper metal and O2 gas. And so what we're going to do is we're going to first, we see that this is data at 25, obviously, so it's going to be off. We're going to go to do we have copper? Oh, shoot. We don't have copper 1 oxide. Do you know why we don't have copper 1 oxide? Because what's the most stable form of copper in under normal conditions? Copper 1 or copper 2? Copper 2. It's like, what's the most stable oxidation state of iron under normal conditions? Iron 2 or iron 3? Iron 3. So rust, iron 3 oxide. Well, I'm going to change this a little bit because we know that the copper 2 oxide is going to suffer the same fate. And so copper 2 oxide here, we're going to go to copper metal plus oxygen gas, and we're going to see what delta G is. Well, I saw what the delta G is over there for 6 whatever, so we're going to do a delta G at 298 Kelvin. And so that's going to be delta G of formation of the products. Delta G of formation of copper, it's an element, and so it's 0. And so the delta G of formation of copper is 0. Delta G of formation of O2. Do I have to scroll to O2? No. You should know the delta G of formation of O2 will be 0. It's an element, an elemental form. Minus the delta G of formation of, this would be the easiest way of calculating delta G, of copper 2 oxide. And so it's a minus, so that gives us plus 129.7 kilojoules. A little bit better at 25 degrees C, but still not spontaneous. This is not spontaneous. However, I think, the temperature, this seems a little bit more spontaneous, so the temperature might not be so high. And so how can we figure out what the temperature is? Because we figured that this is going to be favorable entropy. So the energy is going up, the entropy is going up, and so let's calculate the temperature. In order to calculate the temperature, I'm going to need my delta H and my delta S. And so we could do that quickly. I might as well just do that right now. The delta H, now this is going to be under standard conditions at 298 Kelvin. And the same thing applies here. And so it's just going to be, the minus of this is going to be plus 157.3. So this is going to be a quick calculation, because both of these are 0. But my delta S is going to be a little bit longer calculation because both of those are not 0. And so I'm going to have to scroll to half an O2. But anyway, I got my copper. The copper is 33.15 joules per mole Kelvin. I have 1 mole, so I'll just call it joules per Kelvin. Plus, the other product is 1/2 O2, 1/2 a mole of O2. I'll have to scroll to the O2. And let's go to the next page here for oxygen, or the next page for oxygen. O2 is 205.1. And so I only have a 1/2 a mole, so the entropy should be half. So this is going to be joules per Kelvin. Minus the entropy of the reactants. So let's go back 2 pages here. And the entropy for the reactants, 42.63. And so we'll continue this next time, joules per Kelvin.
All right, let's stop here.